Hey everyone, welcome back for another deep dive. Today we are taking a look at a paper called Leveraging Combinatorial Testing for Safety-Critical Computer Vision Datasets.
Yeah, it's a really interesting paper that tackles a pretty big challenge. It's all about how we can thoroughly test perception functions for things like autonomous driving.
Right, because obviously in those kinds of applications, safety is absolutely critical. I mean, lives are at stake.
Absolutely. And one of the key points the authors make is that traditional software verification techniques just don't quite cut it when it comes to deep neural networks.
They're kind of fundamentally different beasts, right? Like
Yeah.
the way we approach testing needs to adapt.
Exactly. Like traditional methods often rely on massive data sets and aggregate statistical results.
But that doesn't really give you the fine-grained level of certainty you need for safety-critical systems.
Right. You need to be able to verify individual tests, not just look at the overall performance.
So they argue for moving away from aggregate statistical results,
Yeah.
instead focusing on verifying each test individually.
Yeah. And they actually use a really compelling example in the paper to illustrate this.
Oh yeah, the pedestrian at the intersection.
Exactly. Imagine a self-driving car navigating an intersection with a pedestrian nearby.
Seems simple enough at first glance.
But when you start to break it down, there's a crazy number of variables at play.
Lighting conditions, weather, the pedestrian's clothing, even other vehicles or occlusions.
Right. All these things can dramatically impact how the car's perception system performs.
And a slight change in any one of these factors could lead to a totally different outcome.
So you can see how quickly it becomes impossible to test every single possible combination.
And that's where combinatorial testing comes in.
Exactly. So combinatorial testing is a technique that's been used in software engineering for quite a while.
And the basic idea is that instead of testing every single permutation, you focus on testing all possible combinations of a smaller number of variables.
Yeah. They call this T-wise testing, where T is the number of variables you're combining at a time.
So you might test all pairs or all triplets of variables instead of every possible combination.
And what's really cool is that even this seemingly limited approach is surprisingly effective.
The paper mentions that testing all pairwise combinations, even with a relatively small number of input parameters, can uncover a huge percentage of potential errors.
It's like getting the most bang for your buck in terms of testing effort.
And they highlight that this approach has a solid track record in other safety-critical fields like spacecraft design and medical devices.
So it's not just some theoretical idea.
Right. Now, to connect this back to computer vision, we need to think about things a little differently.
So in combinatorial testing, a test suite is basically a set of images, and each image represents a specific combination of variables.
Instead of testing code inputs, you're testing combinations of image features.
Exactly. But then the question becomes, how do we actually define all those variables and their possible values for something as complex as a visual scene?
We need some way to systematically break down the visual world into these testable chunks.
Right. And to tackle this, the authors introduce a tool called Scode Analyzer.
Okay, and Scode Analyzer helps experts define what they call a visual domain model.
Yeah, basically, it helps you identify the key factors that are relevant in both the operational domain, so the context of the scenario.
And the visual effects that could influence perception.
Exactly. So like for our intersection example, Scode Analyzer would help us define factors like time of day.
With options like morning, afternoon, or night.
Right. Or weather, with options like clear, rainy, or foggy.
But it's not just a simple list of variables, is it? Scode Analyzer lets you do more than that.
You're right. It also allows you to incorporate constraints.
So these constraints capture real-world relationships between those factors.
Exactly. Like you could specify that wet or icy road conditions are almost always going to lead to reflections on the road surface.
Which helps to refine the model even further and reduce the number of test cases you need to consider.
It's all about creating a model that actually reflects the complexities of the real world.
And they give a great example of this with their vulnerable road user scenario.
VRU for sure.
Yeah, they model a scenario where a child is jaywalking at an intersection. And they break it down into factors like the time of day, the weather, the road conditions.
And even the type and pose of the VRU, like is it a child running or an adult walking?
And how much contrast there is between the VRU and the background.
It really highlights how many variables are at play, even in a seemingly simple situation.
Now, they actually took 8 existing test cases that were based on simulated driving sequences and used those as a starting point.
Right. Kind of like leveraging the data they already had.
And then they used a tool called PICT, which is a combinatorial testing tool, to analyze those existing test cases.
And figure out what additional test cases they needed to achieve complete pairwise coverage.
So PICT is like saying, okay, you've got these 8 cases. Now here are 15 more you need to create to cover all the pairwise combinations of those variables.
Exactly. And this actually brings up a really important point that the authors emphasize. Even if you have a large data set, if it's collected randomly or without this structured approach, it often fails to achieve complete T-wise coverage.
Especially as you start to increase the value of T and look at combinations of 3 or more variables.
They even ran an experiment to simulate this untargeted data collection using random sampling.
And they found that even with 100 randomly generated test cases, they didn't always achieve full pairwise coverage. So even with a lot of data, you're not guaranteed to be testing all the important combinations.
Exactly. And that's the power of combinatorial testing.
Yeah.
It gives you a systematic and efficient way to build a really robust test set, and it ensures that you're covering those critical combinations of variables.
Okay, so let's recap the workflow they propose.
Right.
First, you define your visual domain model using SCODE and make sure to include those constraints that capture the real-world relationships.
Yeah.
Then you take that model and export it into PICT.
Right.
And PICT does its magic and generates a set of abstract test cases, which are essentially just combinations of those variables.
Then you take those abstract test cases and map them to concrete images. And that might involve selecting images from existing data sets, synthesizing new images, or some combination of both.
So it's flexible. You can tailor it to fit your specific needs and resources.
Exactly. And that's one of its biggest strengths.
Now, I'm curious about how this approach handles those situations where you need to add new dimensions to your model.
Like, what do you do if you've already created your test set and then realize you need to add something like road friction to the model?
Do you have to start over from scratch?
That's a great question, and the authors address this with the idea of incremental data generation.
Okay, so you can add new dimensions without having to rebuild the entire test set from the ground up.
Exactly. They even give an example where they add road friction to their existing road plus lane model. And even with this new dimension, the number of test cases didn't increase dramatically, especially when they use their existing data as a starting point.
So it's like building on a solid foundation. You don't have to tear down the whole house every time you want to add a new room.
I like that analogy.
We've covered a lot of ground already,
I have.
but we've only scratched the surface of what this paper has to offer. There's still more to unpack.
I like how this approach can be used to analyze existing data sets.
Stay tuned for part 2, where we'll dive into that and more.
Welcome back. Let's dig into how this combinatorial testing idea can actually be used to analyze existing data sets.
This is what I'm really curious about.
Yeah.
We talked about building these really robust test sets, but what about the data sets we already have? The huge ones that researchers are already using. Can we use this approach to understand those data sets better?
Absolutely. And one of the coolest things about this paper is that they actually apply this approach to analyze the cityscapes data set.
Ah, cityscapes.
Yeah.
The classic data set for urban scene understanding.
Yeah, it's huge and widely used in research.
So what did they do? Did they go through and manually annotate every image with all the different variables?
That would have been a massive undertaking. No, they actually used the existing semantic segmentation maps as a proxy for metadata.
Okay, so those are the pixel level labels that identify different objects in each image.
Right. So instead of having to annotate everything from scratch, they leveraged the information that was already there.
Smart.
And by analyzing the coverage of different semantic classes and their combinations, they could identify potential gaps in the data set.
Wait, so you're telling me that even a data set as big and well-established as cityscapes has blind spots?
It does, and that's a really important point. Their analysis found that certain dimensions like ego vehicle and license plate were underrepresented in their interactions with other variables.
So those elements might be present in the data set, but they might not be showing up in all the relevant combinations with things like weather or time of day or road type.
Exactly. And this kind of insight is super valuable because it helps researchers understand the limitations of the data they're working with.
It's like a quality control check for your data.
Yeah, I like that. And it allows you to make more informed decisions about how to augment your data or collect more data in a targeted way.
So it's not just about the size of the data set anymore. It's about understanding how comprehensive it really is.
Right. And they actually did a similar analysis on the AEV dataset, which is even larger than cityscapes.
AEV.
It stands for A3D Extended Version. It's a dataset for autonomous driving with over 10,000 images.
10,000. And it still wasn't fully covered.
Surprisingly, no. Even that massive dataset didn't achieve full pairwise coverage.
So size isn't everything.
Nope. And the AEV analysis actually pointed to some specific classes that were particularly challenging. Things like raindrop, speed bump, and ego car were underrepresented in their interactions with other factors.
So that gives you a starting point for improving the data set, right? Like you know where to focus your efforts.
Exactly. It's like a roadmap for targeted data augmentation or collection.
This whole thing with combinatorial testing for analysis is really blowing my mind.
It's a powerful tool. And it really highlights the shift in how we think about data sets. It's not just about quantity anymore. It's about quality and targeted coverage.
I'm already thinking about how I can apply this to my own work.
Me too.
Are there any other key takeaways from this part of the paper that you think are worth highlighting?
I think the biggest one is that this approach isn't just for creating new data sets. It can be just as useful for understanding the data sets we already have.
It's about moving beyond just a gut feeling about our data and actually being able to quantify things like coverage and identify areas for improvement.
And that's crucial for anyone working with computer vision data, especially in safety-critical applications.
So what's next? Where do we go from here?
Well, we've talked a lot about the technical details, but I think the real question is how can our listeners apply these ideas in their own work?
Yeah, our listeners are experts in mathematics, machine learning, and data science. How can they take these concepts and make them actionable?
That's a great question, and I think it's the perfect segue into our final part.
Okay, so let's bring it all together. We've really dug into this idea of combinatorial testing and how it can completely change how we approach both creating A&D, analyzing data sets. But I'm thinking about our listener right now, someone who's deep in the world of machine learning and data science. What's the takeaway for them? How can they actually use these ideas in their work?
Yeah, that's the key question, isn't it? I think the first thing is we need to shift our mindset a bit. Move away from this idea that bigger data sets are always better.
It's about being more strategic with our data.
Exactly. We need to understand the problem we're trying to solve really deeply and identify the variables that really matter.
And how those variables interact with each other.
Right, and that's where domain modeling comes in. Tools like Scode Analyzer might be specific to visual domains, but the principle behind them is much broader. We need to be really explicit about modeling the factors that are relevant to our problem.
Including any constraints or dependencies between those factors.
Exactly. So before we even start collecting data, we need to have a solid understanding of what we're trying to capture.
And then instead of just randomly sampling data or hoping for the best, we can use these combinatorial testing techniques.
Tools like PICT might not be applicable in every single domain, but the core idea of T-wise testing is incredibly powerful.
It's all about being smart about how you select your data points to make sure you're covering those crucial combinations of variables.
Especially the ones that might be rare but really important for certain applications like safety-critical systems.
Yeah, think about something like anomaly detection. The events you're trying to detect are by definition uncommon. So if your training data doesn't include those rare combinations, you might completely miss them.
Exactly. And I think this whole approach brings a new level of rigor to how we create and analyze data sets.
It feels very scientific and methodical, which I think is something we need more of in the field.
I agree. And it has huge implications for the reliability and trustworthiness of the models we build.
It's not just about getting a good score on some benchmark. It's about building systems that we can actually rely on in the real world.
Especially in situations where the stakes are really high.
And this aligns really well with the growing emphasis on explainability and robustness in machine learning.
We can't treat our models like black boxes anymore.
We need to understand how they work and why they make the decisions they do.
Right. And what I find really exciting about this approach is that it can help to democratize access to high-quality, reliable systems.
So smaller teams with fewer resources can still create robust data sets and models.
They don't have to be at a disadvantage just because they don't have access to massive amounts of data.
It levels the playing field a bit.
Yeah, and that ultimately leads to more innovation and benefits everyone.
So as a final thought, what would you say to our listener who's eager to put these ideas into practice?
I'd say focus on the principles first, Think about the key factors that influence your model and how you can ensure your data captures those factors effectively. And don't be afraid to experiment with different techniques and tools to find what works best for your specific problem.
It's about asking the right questions and being intentional with our data.
Exactly. And by doing that, we can make a real difference in the quality and reliability of the models we build.
And ultimately have a bigger impact with our work.
Absolutely.
Well, that brings us to the end of another deep dive. We hope you found this episode insightful, and we encourage you to explore these ideas further.
And as always, keep learning, keep questioning, and keep pushing the boundaries.
Until next time.